Today we are going to discuss hyperfine splitting under atomic molecular physics. So we have discussed fine structure splitting. Today we are going to discuss hyperfine splitting. So what is hyperfine splitting? So hyperfine splitting is due to the interaction with the total angular momentum, it's the total angular momentum J and the nuclear spin angular momentum I. Okay, and when we say there is interaction between the total angular momentum and the nuclear spin angular momentum, that means there is a nuclear magnetic moment. So the nuclear magnetic moment mu I is given by Gi. This is the G factor for the nucleus into E by 2s mp into I vector. So this is mp means mass of the proton. Just like in when we are dealing with spin of the electron, we introduced Bohr magneton. Spin of the electron or the angular momentum, orbital angular momentum of the electron, we introduced Bohr magneton. Here we introduce a new name which is called nuclear magneton. Here mp is the mass. So you can see that the mass of the proton is much greater than the mass of the electron. So what you have is that this quantity is very less. It's much smaller than the Bohr magneton, and hence you can say the nuclear magnetic moment is very less. So because of this, we can now define what is the total angular momentum, which is due to J and I. So J vector plus I vector gives us the total angular momentum of the atom, and that is given by the value. So total angular momentum is given by the value F into F plus 1 H cross. And the selection rule in this kind of situation, which involves hyperfine splitting, involves delta F, which is 0 or plus minus 1. So this is the selection rule. So we'll consider a problem here. So in this problem, show that the energy interval between two hyperfine levels F and F plus 1 is proportional to F plus 1. This is something like Landy interval which we have done. So here energy for any hyperfine level which is defined by F. Okay, F is similar to this F. Okay, it is similar to this F. So it is given by, so this is actually your, this is actually F square. This is like total angular momentum square. This is the total angular momentum square of the, or total spin angular momentum square of the nucleus, and this is the total angular momentum square of the atom, where we have not taken into consideration the nuclear spin. So this is easy to do. So this is EF. So we can also find something like E. Okay, E F plus 1, and once we can find E F plus 1, so F plus 1, okay, and then we just have to subtract EF plus 1 minus EF, and we should get the answer. Next we go to hyperfine this problem. The number of hyperfine components observed in the transition this to this is the spectroscopic notation, 2d3 by 2 to 2p half for an atom with nuclear spin I is equal to 3 is, so how many, so the question is how many such splittings, how many such hyperfine transition lines we are going to see. So this is my J, right? This is the J, value of J in this spectroscopic notation, and here the value of J is half. Okay, the stylus is giving problem, so I'm sorry for that. So here this spectroscopic term will be divided into these 4 levels. 1, so this is one level, this is one level, this is one, and this is another, because here I is equal to 3, so from 3 minus 3 by 2, which is 3 by 2, to 3 plus 3 by 2, which is 9 by 2. So we will have 4 splittings of this level. Similarly, this level will be split into 3 minus half, it is 5 by 2, and is 5 by 2, and 3 by 2 plus, so 3 plus half, which is 7 by 2. So these splittings are there, and I have drawn the transition lines. So initially, if we work with a spectrometer with low resolving power, we will see only this kind of transition, one line, okay, sorry, one line. But if we use a very powerful spectrometer, then we will see this one line is actually divided into, how many lines are there? So there are 6 lines. So due to hyperfine splitting, the number of hyperfine components observed here will be 6, and you have to follow the selection rules. So using the selection rules that we had discussed before, so delta F, we have to be careful about delta F is equal to, which we had discussed before. So what are the delta F's? We have delta F is equal to 0 and plus minus 1. Obeying these rules, we can find out what are the transitions that are taking place. Next we have this problem. The total spin of a hydrogen atom is due to the contribution of the spins of the electron and the proton. in the high temperature limit, the ratio of the number of atoms in the spin 1 state to the number in the spin 0 state is this. So how many atoms will be in spin 1 state and how many atoms will be in spin 0 state? The ratio of those, we want the ratio of that. Number of atoms in the S1 state to the number of atoms in the spin 0 state. Okay. So, and high temperature limit means, what does high temperature limit means? The higher energy state. So the higher energy state and the lower energy state have equal probability of occupation. If it was not a high energy state then low energy state, then the problem would have been approached differently. So for F is equal to 0, so we have one electron, one proton. So the proton is coming from the nucleus. So F is equal to 0, the two states F is equal to 0 or F is equal to 1. When F is equal to 0, the degeneracy is 1. That is, corresponding to F is equal to 0, there can be only one state. While when F is equal to 0, F is equal to 1, the degeneracy is 3. Okay, here degeneracy is 3. So the number of atoms having F is equal to 1 to number of atoms having F is equal to 0 is basically will be the ratio of the degeneracy. Okay, so it will be 2F plus 1 at F is equal to 1 and this is 2F plus 1 at F is equal to 0. Okay. So the effective spin-spin interaction between the electron spin Sc and the proton spin Sp, okay, in the ground state of the hydrogen atom is H prime A Sc dot Sp. Okay, so this is the spin-spin interaction between the nuclear spin and the spin of the electron. So the energy difference between the levels due to hyperfine splitting. So because of this interaction H prime, the ground state will be split into two levels. So what is the energy difference between the levels due to hyperfine splitting? So here F means the total angular momentum including the spin. We are considering spin here, spin of the nucleus. So it will be 0 and 1. So A Sc dot Sp is, we know, is equal to F square. By F square I mean F square, not minus S square E minus S square P. Here F square means actually F square, if I write F square, it actually here I mean, sorry, this is really giving trouble. F square is actually F into F plus 1. F into F into F plus 1. Then F into F plus 1 H bar square. So when I write S square E, that means half into half plus 1 H bar square, and S square P is half into half plus 1 H bar square. Okay. So this is this. So you have to evaluate this quantity at F is equal to 1. This quantity, which we had already written before, and this quantity we have to evaluate at F is equal to 0 and subtract this from this, and we should get the answer. You can check H bar square. So remember that F square is not actually like, then it should be like 0 or 1. F square by F square, I mean this quantity. Okay, so let me just go to red. So F square is like this. Okay, this is F square. So I'll stop here today, and very soon we'll start with the next topic under atomic and molecular physics.